The particle lived for less than a trillionth of a second. 23 years passed before anyone could prove it had lived at all. Not for lack of trying. 4 separate experiments ran dedicated searches across 2 continents. Physicists built analysis chains from nothing, trained selection algorithms on simulated events, combed through datasets representing years of accumulated collisions, and found nothing. Or found something that looked like nothing. Or found something that looked like something but collapsed under scrutiny, which in the language of particle physics occupies a particular kind of limbo, not confirmed, not refuted, just suspended in the literature, unresolved, exerting a quiet gravitational pull on every search that came after it. The particle is called the GCC+. If you need to say it aloud, G, like the Z in zoo followed by a quiet I, then CC for 2 charm quarks, then plus for its electric charge. Nobody outside particle physics will call it that. Every news story published in the week of March 17, 2026, called it a heavy cousin of the proton, which is accurate enough to be useful and imprecise enough to miss what makes it strange. What makes it strange is not its weight. It is what the weight costs, what it means to put charm quarks inside a baryon, what that does to the internal dynamics, what it demands of any instrument that wants to see the thing before it disappears. So let me start at the beginning, not the announcement. Let me start with the proton. A proton contains 3 quarks, 2 up quarks and 1 down quark, held together by the strong nuclear force, the most powerful fundamental force in nature, the force that confines quarks permanently, that has never once allowed a free quark to be observed, that acts through particles called gluons which carry what physicists call color charge, the strong force equivalent of electric charge. Though the word color has nothing to do with visible light, and was chosen simply because the mathematics needed 3 kinds, and physicists decided to call them red, green, and blue. Up quarks and down quarks are the lightest quarks that exist. They weigh almost nothing individually. The up quark weighs approximately 2 mega-electronvolts, roughly 0.004% of the proton's total mass. The down quark weighs approximately 4.5 mega-electronvolts. The proton, by contrast, weighs approximately 938 mega-electronvolts. The quarks inside it account for perhaps 1% of its mass. The remaining 99% comes from the churning, seething energy of the gluon field that holds them together, the binding energy of the strong force, manifesting as mass through Einstein's equation in a way that is clean and exact and still slightly astonishing when you sit with it. The proton is one of the most stable objects in the known universe. A free proton, left completely alone, does not decay. Physicists have spent decades searching for proton decay, building underground tanks filled with thousands of tons of ultra-pure water, surrounding them with arrays of photomultiplier tubes, waiting for the faint flash of light that would mean a proton had finally given way. They have found nothing. The lower limit on the proton's lifetime is currently around 10 to the 34th years, a number so large it has no useful comparison in the observable universe, which is itself only about 14 billion years old. The proton is, for all practical purposes, permanent. The GCC+ takes that proton and replaces the 2 up quarks with charm quarks. That is the entire structural change written in 8 words, but those 8 words contain the whole problem. Charm quarks are not slightly heavier than up quarks, the way a heavy coat is slightly heavier than a light one. They are approximately 1,300 times heavier. Each charm quark carries a mass of roughly 1.27 giga-electronvolts, meaning each charm quark alone is more massive than the entire proton. Putting 2 of them inside a baryon does not produce a heavier proton the way substituting a lead weight for a tennis ball produces a heavier racket. It changes the internal dynamics entirely, at the level of the forces and timescales involved, in a way that has no simple analogy because the analogy would need to be quantum mechanical to be accurate. The particle that results weighs roughly 3,620 mega-electronvolts, about 4 times the proton mass. It lives for an almost incomprehensibly short time, and it decays through a cascade of lighter particles that a detector must reconstruct backward like reading dispersing smoke to find where a brief fire burned. Less than a trillionth of a second. Hold that not as a number but as a physical fact. A trillionth of a second is 1 picosecond. Light travels roughly 0.3 of a millimeter in 1 picosecond. The GCC+, moving at a significant fraction of the speed of light inside the accelerator's beam pipe, travels a distance in its entire lifetime that is smaller than the diameter of a human hair. The detector does not see the particle. It sees the ghost of the decay, the trajectories of the lighter particles that the GCC+ became when it ceased to exist. And from those trajectories, working backward through the geometry and the momenta and the particle identities, and the angles of light emitted in a radiator medium, it reconstructs what was there a fraction of a moment before. Not the particle. The aftermath of the particle. The shadow it left in a detector designed to read shadows. The particle had a predicted lifetime up to 6 times shorter than that of its already fleeting partner, the GCC++, which was itself discovered only in 2017 and lives for only about 1 trillionth of a second before decaying. That factor of 6 is not an approximation or a rough estimate. It comes from a specific quantum mechanical effect involving the way the down quark inside the GCC+ interferes with the decay pathways of the charm quarks, a process called Pauli interference, in which the quantum numbers of the participating quarks create destructive interference that accelerates the overall decay rate in a way that is exactly calculable and deeply resistant to intuition. Change 1 quark. Lose 6 times the lifetime. The mathematics is consistent. The physical feeling of it requires accepting that quantum interference is not a correction layered on top of classical behavior. It is the behavior. There is no underlying classical picture that makes this sensible. The interference is the physics, all the way down. For the experimentalists who spent careers searching for this particle, the consequence was direct and specific. The GCC+ would spend even less time in existence than its partner before decaying into daughter particles. The point in space where the baryon ceases to exist and its decay products begin separate trajectories, the decay vertex, would be even closer to the production vertex than for the GCC++. Reconstructing the event would require measuring the positions of particle tracks with precision beyond what the previous generation of detectors could reach, distinguishing the decay vertex from the production vertex by a distance that can be smaller than a human cell. Not smaller than a hair, smaller than a cell. The detector needed to be rebuilt, and before that became possible, 23 years passed. To understand what the search looked like during those 23 years, you need to understand what charm quarks are in a deeper sense than their mass. Charm was predicted before it was discovered. In 1970, 3 physicists, Sheldon Glashow, John Iliopoulos, and Luciano Maiani, proposed the existence of a 4th quark, beyond the 3 then known, as a way of resolving a specific theoretical inconsistency in how the weak force appeared to operate. Their proposal is known by their initials as the GIM mechanism, and it required charm to exist in order for certain decay processes to be suppressed in a way that matched the experimental data. Charm was theoretically mandatory for the standard model to be consistent. It arrived, confirmed experimentally, in November 1974, simultaneously, at 2 different laboratories in the United States, in the form of a new particle called the JPC, which was a bound state of a charm quark and its antimatter partner. The simultaneous discovery at Stanford and at Brookhaven, communicated across the country on the same day, became known as the November Revolution in particle physics. 2 Nobel Prizes followed. Charm was real. What charm means practically is instability. A charm quark does not exist indefinitely. It decays through the weak force into a strange quark, shedding mass as energy in the form of a W boson, which itself decays into lighter particles. The timescale for this decay is short. Not as short as the GCC+ lifetime, which involves the entire baryon collapsing, but short enough that any hadron containing charm quarks is unstable by definition. The charm quark carries a quantum number, called, unsurprisingly, charm, that is not conserved by the weak interaction. If charm were conserved the way electric charge is conserved, a charmed hadron would be as stable as a proton. Instead, charm bleeds away through weak decays, and the particles that carry it live for a trillionth of a second or less before becoming something else. Two charm quarks inside a single baryon multiplies this instability in a way that involves not simple doubling but interference. For the GCC++, two charm quarks and one up quark, the interference effects between the two charm quarks' decay pathways and the up quark spectator produce one balance of contributions. For the GCC+, two charm quarks and one down quark, the balance shifts. When the charm quarks decay through the weak interaction they produce, among other things, up quarks. In the GCC++, the baryon already contains an up quark, but the two up quarks can occupy different quantum states, different spin orientations, different color states, and coexist without conflict. In the GCC+, the destructive interference between the decay-produced up quark and the various intermediate states creates an effect that physicists call Pauli interference, the quantum exclusion that forbids identical fermions from sharing the same quantum state generates destructive interference in the decay amplitude, opening additional fast decay channels that accelerate the lifetime by a factor of roughly 6. Change one quark, up to down, gain one factor of 6 in decay rate, lose 6 times the lifetime. The mathematics produces this exactly. There is no classical picture that illuminates why it should be so. There is only the calculation which is consistent, and the experimental result, which confirmed it in March 2026. The first serious experimental claim for the GCC+ came in 2002 from an experiment called CELEX at the Fermi National Accelerator Laboratory in Batavia, Illinois. CELEX was a fixed target experiment that used a 600 giga-electron-volt charged hyperon beam, a beam of heavy, strange baryons accelerated to enormous energies, directed at thin foil targets made of copper and diamond. The collaboration was looking for doubly charmed baryons, which at that time had never been experimentally observed. They found what appeared to be a signal in the decay mode GCC+ to lambda C plus K minus pi plus. They reported it at 4.7 sigma. They reported the mass of their candidate particle at approximately 3,520 mega-electron-volts per speed of light squared. 4.7 sigma sounds enormous if you are accustomed to other scientific disciplines. In most fields of science, a result with a 1 in a million probability of being a random fluctuation would constitute definitive evidence. Particle physics adopted a 5 sigma standard specifically because its datasets are so large that the look elsewhere effect, the statistical penalty for searching in many mass hypotheses, many decay channels, many selection configurations simultaneously, can inflate apparent significances in ways that are difficult to fully account for after the fact. The field had learned, through decades of near discoveries that dissolved upon replication, that 1 in a million is not safe enough. 5 sigma, roughly 1 in 3.5 million, became the threshold not as a rigid law, but as accumulated institutional wisdom. CELEX's result sat at 4.7, below threshold, not a discovery. A hint at the edge of significance, the kind of result that demands confirmation and receives, instead, years of silence. The silence arrived in installments. Focus searched and found nothing. Focus was a fixed target experiment at Fermilab using a photon beam, well suited to finding charmed mesons and some charmed baryons, but its sensitivity to a doubly charmed baryon with a lifetime as short as the GCC+ was limited. Baybar searched and found nothing. Baybar was an electron-positron collider experiment at the Stanford Linear Accelerator Center in California, running at the energy of the Upsilon 4s resonance, a threshold energy optimized for producing pairs of B mesons, not for producing doubly charmed baryons at the rate the LHC would later produce them. Bell searched and found nothing. Bell was Baybar's counterpart at the Keck Laboratory in Tsukuba, Japan. operating in a similar energy regime with similar limitations. And LHCb, through its entire Run 1 and Run 2 data collection periods, through years of proton-proton collisions at energies ranging from 7 to 13 tera-electronvolts, through a dataset vastly larger than anything CELEX had accumulated, found nothing. Each null result added to the case against the CELEX claim without formally closing it. The CELEX result was not retracted. It remained in the physical review letters, accessible and citable, formally unresolved, a number at the edge of significance that the field had not confirmed, but had not officially discarded. And the null results piling up around it were not unambiguous refutations, because each null result meant different things depending on the instrument that produced it. If your detector cannot see the particle even if it is present, because the particle's lifetime is too short for your vertex resolution, because the decay products are too difficult to reconstruct with your particular geometry and trigger architecture, because the hardware filter that decides which events to save discards the relevant events before they reach the reconstruction, then your null result is silence rather than refutation. And silence and refutation look identical from the outside, even though they have entirely different implications. The CELEX number sat in the literature for 23 years. Unconfirmed. Unretracted. A coordinate, 3,520 mega-electronvolts, that shaped how physicists designed subsequent searches, weighted their analysis windows, and allocated the limited statistical power of their datasets. The number was wrong, but nobody could prove it was wrong until the right instrument was built and the right measurement was made. In 2017, the right measurement began to approach, though it did not arrive. LHCb announced the discovery of the GCC++, 2 charm quarks and 1 up quark, at a mass of 3,621 mega-electronvolts. The partner particle, the one that differs from the GCC+ only in whether it contains an up quark or a down. The theoretical prediction for the mass splitting between these two particles, the difference in mass that arises from the mass difference between up and down quarks plus small electromagnetic corrections, is a few mega-electronvolts at most, which means that if the GCC++ sits at 3,621, the GCC+ should sit within a few units of that number, not 100 mega-electronvolts below it. The CELEX candidate sat at 3,520 mega-electronvolts, 100 mega-electronvolts below the GCC++. This discrepancy is not a rounding error. It is not a calibration offset that might dissolve with additional scrutiny. It is 100 mega-electronvolts, which in this context is a physically meaningful gap that means one of exactly two things. Either the CELEX result was statistical noise that happened to produce a peak in the wrong place, or the CELEX experiment found a completely different particle. The theoretical prediction is clear. The GCC+ and the GCC++ should be within a few mega-electronvolts of each other. They differ by 1 quark substitution, up for down, with a predicted mass consequence of single-digit mega-electronvolts. Not 100. The CELEX number was wrong, but in 2017, with the partner particle confirmed, LHCb still had not found the GCC+. They had found its partner and noted the discrepancy with CELEX, which put additional pressure on the original claim without delivering the definitive observation that would end the question. The question required 9 more years. It required a rebuilt detector. It required a specific sequence of engineering decisions made in an underground cavern near Geneva that would change what the instrument was capable of reading from the collisions it was recording. Before the machine, the physics. Because the reason the machine needed rebuilding is inseparable from what is actually inside the GCC+, and what is inside it is not simply quarks arranged in a proton-like configuration with heavier components. The structure that forms when 2 charm quarks and 1 light quark assemble inside a baryon is something subtler than that. Inside an ordinary proton, all 3 quarks have roughly comparable masses. The up and down quarks are so close in mass, 2 versus 4.5 mega-electronvolts, that the dynamics are genuinely three-body. No single pair of quarks dominates over the third. The binding energy is distributed across the system. Calculating the proton's properties from first principles using quantum chromodynamics requires numerical methods running on supercomputers for months to produce a single reliable number, and the results still carry significant uncertainties. The proton is one of the simplest composite objects in nature, and one of the most computationally difficult to calculate from scratch. In the doubly charmed baryon, the situation changes. Charm quarks are heavy enough, 1.27 giga-electronvolts each, compared to 2 to 4 mega-electronvolts for the up and down quarks they replace, that they move relatively slowly with respect to one another compared to the light quarks in ordinary baryons. In the language of quantum field theory, the two charm quarks are non-relativistic to a good approximation. This means they can form a relatively compact bound state within the baryon, a pair, called a diquark, held together by the color force, that carries a specific color charge and sits near the center of the baryon while the lighter down quark moves in the color field the diquark generates. The structure that results has two scales. At the short distance scale, the two heavy charm quarks interact with each other in a way that is calculable by techniques borrowed from the theory of heavy quark-bound states. At the longer distance scale, the light quark orbits the diquark in a way that is analogous, in some respects, to an electron orbiting a heavy nucleus, not identical. Because the light quark is still relativistic and still feels the confining force, but analogous in the sense that the hierarchy of masses allows the dynamics to separate. The result is a system that is fundamentally more tractable than an ordinary baryon, more amenable to precise theoretical prediction, more useful as a test of the theory precisely because the calculation can be factored into pieces that different theoretical tools can handle. Tim Gershon at the University of Warwick described this as providing an ideal way to test QCD, quantum chromodynamics, the theory of the strong force. What he meant is that QCD is correct. Every experiment that has tested it has confirmed it, but correct and fully understood are not the same thing. The strong force is extraordinarily difficult to calculate in the regime where it matters most, the low-energy regime where quarks are confined inside hadrons, where the interaction is too strong for perturbation theory to work, where the only reliable method is numerical simulation on a lattice. The doubly charmed baryon, with its separable scales and its unusual internal structure, provides a particularly clean environment to test whether the lattice calculations are capturing the physics correctly, because the theoretical prediction is more precise here than for ordinary baryons, and the experimental measurement can be compared against it at a level of detail that would reveal discrepancies if they exist. This is the deeper meaning of the GCC plus discovery, not just that a new particle was found, that a new testing ground for QCD became available, and that the ground itself is shaped by a structure that the standard model has predicted in detail, but never before been able to test at this level of precision. Juan Rojo, at Vrije University Amsterdam, was honest about where that testing ground currently stands. He said, speaking to New Scientist the week of the announcement, the data is now ahead of the theory for these kinds of particles. The experimental results are arriving, the Shy CC++ in 2017, the Shy CC+ in 2026, before the theoretical tools to fully exploit them have been developed. In 5 years, he said, this measurement might be able to answer some very important theory questions, such as what different combinations of quarks mean for particle masses, how the strong force responds to the substitution of heavy quarks for light ones, whether the lattice calculations are correctly predicting the hierarchy of properties across the doubly charmed baryon family. In 5 years, if the theory catches up, if the calculations become precise enough, if the measurements of the lifetime and the decay channels and the production cross-sections are completed, 5 years. The present detector will still be running in 5 years, collecting data, accumulating events. Whether the detector that follows it, the one designed to collect tens of thousands of doubly charmed baryons per year rather than hundreds, the one designed to push into the regime of beauty charm and doubly beauty baryons, where the really stringent tests of the theory become available, Whether that detector gets built depends on decisions being made in funding offices that are a long way from Geneva. Those decisions had already been made, in a direction that Gershon called a complete shock, before the GCC Plus announcement arrived. The detector that found the GCC Plus in 2026 did not exist in its current form 3 years earlier. The LHCb detector has been operating at the Large Hadron Collider since 2010. It is built in a cavern approximately 100 meters underground near Ferney-Voltaire, France, in a region where the LHC tunnel crosses the French-Swiss border. The detector is long and narrow, approximately 20 meters in length, designed in what physicists call a forward spectrometer geometry. Instead of surrounding the collision point from all sides the way a traditional collider detector does, LHCb captures particles produced at small angles to the beam direction, in a cone forward of the interaction point. This geometry is not a compromise or a budget constraint. It is a deliberate choice, because beauty quarks and charm quarks produced in high-energy proton-proton collisions are concentrated at small angles to the beam. The forward geometry catches them preferentially. It is the reason LHCb has over 800 publications to its name, has discovered tens of new hadrons including pentaquarks and tetraquarks, and the first observations of CP violation and charm decays, and is the only instrument of its kind currently operating. The original detector, which ran through 2018 before being shut down for upgrades, was designed for a luminosity significantly lower than the LHC could deliver. To protect the detector from radiation damage and to keep the data rate manageable, LHCb ran at a fraction of the available collision rate. The upgrade, completed in 2022 and 2023, was designed to change this fundamentally. The new LHCb processes 5 times more collisions per second than its predecessor and reads out every single one. To understand what that means in practice, start with the hardware trigger. The original LHCb had a hardware stage, custom electronics that made decisions at 40 MHz, selecting which events to pass to the software reconstruction and which to discard. Making decisions at 40 million per second requires using only the simplest information: a muon above a certain momentum threshold, a cluster of calorimeter energy above a certain value. For the kind of hadronic final states that the GCC Plus produces, multiple charged tracks emerging from a decay vertex displaced from the production vertex by a distance measurable only in microns, the hardware trigger was not capable of making reliable decisions. It discarded events, not randomly, systematically, in a way that reduced the effective dataset for hadronic charm physics compared to what the raw collision rate could have provided. The upgraded trigger removes this bottleneck. There is no hardware stage. Every bunch crossing, every collision event is read out at the full rate and passed directly to a computing farm that performs a full software reconstruction in real time. The farm runs track-finding algorithms, vertex fitting procedures, particle identification comparisons, invariant mass calculations, all of it, on every event, fast enough to keep pace with 40 million crossings per second. Selection decisions are made based on the fully reconstructed event, rather than a partial hardware summary. For hadronic signal modes like the GCC Plus decay chain, the efficiency improvement is substantial. Events that would have been discarded at the first filter are now reconstructed completely, and the decision about whether they are interesting is made with full information. But the trigger change, transformative as it was, operated in partnership with a second change that was even more fundamental for the GCC Plus specifically. The vertex locator, the VLO, the innermost layer of the LHCb detector, was replaced entirely. The original VLO was a silicon microstrip detector. Strips measure position in one transverse dimension well and the orthogonal dimension poorly. Combining strip orientations to get two-dimensional position measurements introduces ambiguities when many particle tracks are present simultaneously, which at LHC luminosities they always are. The spatial resolution of a strip detector is limited by the strip pitch, the spacing between strips, and by the geometry of how the strips are arranged. The upgraded VELO is a silicon pixel detector. Each pixel is 55 micrometers on a side, just over half the width of a human hair individually. The pixel detector measures position in 2 dimensions simultaneously, without ambiguity, at a granularity the strip detector could not approach. In the language of spatial resolution, the upgraded Velo can determine where a charged particle crossed the detector to within roughly 4 micrometers in the best cases. 4 micrometers is 4/1000ths of a millimeter. It is the width of a red blood cell, roughly. It is the precision needed to distinguish a decay vertex from a production vertex for a particle that travels a distance smaller than a cell wall before decaying. The Velo operates 5 millimeters from the beamline. In the geometry of large particle physics detectors, which typically begin their sensitive volume at distances of several centimeters from the interaction point, 5 millimeters is aggressive. It is aggressive by design. The closer the detector is to the production vertex, the better it can resolve the displacement of decay vertices for short-lived particles. 5 millimeters is the minimum distance at which the Velo can operate while retracting sufficiently to allow beam injection, and then moving back into position once stable beams are established. A mechanical operation performed automatically at the start of each LHC fill cycle. Maintaining a silicon pixel detector at 5 millimeters from the LHC beamline, operating continuously during physics runs, requires engineering solutions that do not exist off the shelf. The radiation dose at that distance is high enough to cause progressive damage to the silicon sensors. The atoms in the crystal lattice are displaced by energetic particles, creating defects that degrade the sensor's ability to collect charge from new particle traversals. The sensors are designed to tolerate this damage over their operational lifetime, but they need to be monitored, and their response characterized as a function of accumulated dose. The readout electronics, custom application-specific integrated circuits, ASICs, designed specifically for this application, need to handle hit rates at 5 millimeters from the beam without saturating, need to survive the radiation environment, and need to transfer data fast enough to match the 40 MHz readout rate of the upgraded trigger. The sensors sit in vacuum, separated from the beam vacuum by a thin aluminum foil, cool enough to slow the radiation damage that accumulates over the running period, mechanically stable enough that their positions can be determined at the micrometer level needed for track reconstruction. The UK was deeply embedded in every part of this. Researchers at the University of Liverpool, the University of Manchester, and institutions across Britain contributed to the design of the pixel sensors, the development of the ASICs, the mechanical engineering of the retraction and positioning system, and the installation work carried out during the long shutdown. The LHCb upgrade was, in a real and specific sense, substantially a British instrument. 4 of the 8 spokespeople the LHCb collaboration has had in its history came from UK universities. More than 18% of the collaboration's researchers are based at UK institutions. The UK is not one participant among many. It has been the technical engine of the experiment for a decade and a half. Beyond the Velo and the trigger, the upgrade replaced the upstream tracker, a silicon detector sitting upstream of the dipole magnet that helps determine track momentum, and upgraded the ring imaging Cherenkov detectors. The rich system is what allows the reconstruction to identify particle species. When a charged particle travels through a medium faster than light travels in that medium, not faster than light in vacuum, but faster than light in the particular radiator material, it emits Cherenkov radiation in a cone whose opening angle depends on the particle's velocity. Measure the angle. Know the momentum from the tracking system. Calculate the mass. The mass tells you whether you are looking at a pion, a kaon, a proton, or something else. For the GCC plus analysis, particle identification at this level matters for a reason that is unglamorous but decisive. The full decay chain ends with 5 charged particles, 1 proton, 2 kaons, and 2 pions. A kaon weighs about 494 mega-electronvolts. A pion weighs about 139. Different enough masses that their Cherenkov angles in the radiator medium differ at the level the rich system can resolve, but only if the photon detectors reading the rings are fast and efficient enough to avoid contamination from out-of-time hits, which in the high luminosity environment of Run 3 would smear the ring reconstruction and degrade the particle identification throughout the tracking volume. The upgraded rich system uses silicon photomultipliers in place of the older multi-anode photomultiplier tubes. Silicon photomultipliers are faster and more efficient. They reduce the contamination from out-of-time hits. The particle identification quality improves throughout the detector. The cation-pion separation that the GCC plus analysis depends on becomes reliable. If the system misidentifies a cation as a pion, the reconstructed invariant mass of a lambda key plus candidate shifts outside the signal window, and the event is lost. If it misidentifies a pion as a cation, a background event can enter the signal region and dilute the significance of the peak. These misidentifications, accumulated across millions of candidates, determine whether 915 events emerge cleanly from background or disappear into it. The discovery is not a single moment. It is a cascade of engineering decisions made by hundreds of people across years, each one removing a small inefficiency or a small source of confusion, each one necessary, none of them individually sufficient, all of them together producing the instrument that found the peak. The photon detector efficiency, the cation-pion separation, the vertex resolution at 5 mm from the beamline, the software trigger that retained the event rather than discarding it, the boosted decision tree trained to separate signal from background, using variables that no individual human intuition could combine as effectively, the blinded signal region, concealed from the analysts until the entire selection strategy had been finalized, preventing the unconscious optimization toward noise that inflates significances in unblinded analyses. All of this together, in 1 year of data collection from a detector that had not existed in its current form until 2023, produced 915 events at 3,619.97 mega-electron-volts, significance 7 sigma, probability of being a random fluctuation less than 1 in a trillion. Tim Gershon, who leads the UK participation in the upgrade, and who takes over as LHCb spokesperson in July 2026, put the comparison plainly. We could observe the GCC Plus in 1 year of data taking, while we had not been able to do so in a decade of data collected with the original LHCb detector. Not a decade of trying and failing, a decade of data collection with an instrument that was approaching but not reaching the sensitivity required. The upgraded detector crossed the threshold. The particle appeared. Chris Parkes at the University of Manchester said, "Not only is it interesting discovering the particle in its own right, the GCC Plus has been searched for a long time, but it also really shows the power that these upgrades to the LHC are having. In 1 year's data sample, we were able to see something that we couldn't see with 10 years of data from the previous generation." Vincenzo Vagnoni, then spokesperson for the LHCb collaboration, said, "This is the first new particle identified after the upgrades to the LHCb detector that were completed in 2023, and only the second time a baryon with 2 heavy quarks has been observed, the first having been observed by LHCb almost 10 years ago." Mark Thompson, CERN's Director General, said, "This major result is a fantastic example of how LHCb's unique capabilities play a vital role in the success of the LHC. It highlights how experimental upgrades at CERN directly lead to new discoveries, setting the stage for the transformative science we expect from the high-luminosity LHC." Transformative. Present tense. March 17, 2026. The science we expect. The upgrade Thomson was gesturing toward, the high-luminosity LHC era, the factor of 10 increase in collision rate, the detector upgrade that would run LHCb at luminosities the current instrument cannot tolerate and collect the data volumes that the current instrument cannot accumulate, had already lost its primary UK funding by the time he spoke. The press release did not mention this. It was left to Gershon in a conversation with Physics World to say it plainly. What Gershon said was specific, and the specificity is worth holding. He said, "These may be out of reach with the current LHCb detector, although we will try our best." He was talking about the heavier cousins, the particles that sit one rung above the Xi in the hierarchy of doubly heavy baryons, the particles whose observation would provide the precision tests of the theory that the Xi discovery makes necessary but cannot by itself deliver. He said, "But we do expect to be able to observe them with a future upgrade called LHCb Upgrade 2. He said, "Unfortunately, the UK funding for this upgrade has recently been put in doubt due to decisions made at the UK funding agency." He said, "This latest result reiterates the uniqueness of LHCb. No other experiment can make these measurements, and the importance of finding a solution to be able to fund LHCb Upgrade 2. No other experiment can make these measurements." That sentence is not a competitive claim. It is a physical description of how the LHCb detector is built and what it is capable of that no other current or planned instrument replicates. To understand what those measurements are and why they matter, why the Xi discovery is a beginning rather than a conclusion, why Gershon used the phrase "try our best" rather than simply saying yes, we will measure those things, requires understanding what the hierarchy of doubly heavy baryons looks like, and what each step up in the hierarchy reveals. The Xi and the Xi are the lightest doubly heavy baryons. They contain 2 charm quarks, the lightest of the heavy quarks. The third member of the lightest doubly charmed baryon family is the omega Cc+, 2 charm quarks and 1 strange quark instead of a down or an up. The omega Cc+ has not been observed. Its predicted mass sits between the Gcc+ and the Gcc++. Its lifetime is predicted by the same heavy quark expansion framework, with a different balance of contributions from Pauli interference and W exchange diagrams that reflects the identity of its strange quark spectator. When the omega Cc+ is eventually found, the 3 measured lifetimes of the 3 lightest doubly charmed baryons, Gcc+, Gc++ omega Cc+, will constitute a test of the heavy quark expansion at a level of detail that is currently impossible with only 2 of the 3 known. But the lightest doubly charmed baryons are only the beginning of the family. The beauty quark, the 5th quark, approximately 4.2 giga-electronvolts in mass, roughly 3 times heavier than the charm quark, is the next step in the hierarchy. A baryon containing 1 beauty quark and 1 charm quark, called the GBC+, would weigh approximately 7 giga-electronvolts and has never been observed. A baryon containing 2 beauty quarks, called the Xi-BB+, would weigh approximately 10 giga-electronvolts and has never been observed. The Xi-CC+ is the lightest accessible member of a family that extends through 2 more generations of increasing mass, each generation providing a more stringent test of the heavy quark expansion, each generation requiring greater detector sensitivity to observe. The heavy quark expansion is a theoretical framework developed over decades that describes how heavy quarks decay inside hadrons. It is tested against charm meson and beauty meson lifetimes, where it has had significant successes. When it is applied to doubly heavy baryons, systems where 2 heavy quarks coexist, where the diquark structure introduces dynamics that do not arise in mesons or singly heavy baryons, the predictions are less well tested. The theoretical uncertainties in the predicted lifetime ratios for doubly heavy baryons are larger than for singly heavy hadrons, in part because the relevant matrix elements have not been computed from first principles to sufficient precision, and in part because the expansion involves contributions from multiple competing diagrams, Pauli interference, W exchange, spectator effects, whose relative sizes depend on the quark content in ways that have not been fully confronted by experiment. Confronting those predictions requires data. Specifically, it requires measured lifetimes for both members of each isospin doublet, compared at a level of precision where the ratio is determined well enough to test the theoretical prediction for the ratio rather than just for the individual values. The ratio is more powerful than either individual number, because systematic uncertainties, calibration effects, efficiency corrections, detector biases tend to cancel in the division. A lifetime ratio measured to 10% tests the theory at a level where the theoretical prediction might be wrong at the 10% level. A ratio measured to 2% tests it 5 times more stringently. Getting from 10% to 2% on a ratio requires roughly 25 times more events. The current LHCb dataset has 915 GCC plus events. That is not enough for a lifetime measurement at the level that would test the heavy quark expansion meaningfully. Full Run-3 data collection will produce thousands of events, perhaps enough for a preliminary lifetime measurement with large uncertainties, enough to confirm the qualitative prediction that the CCC+ is shorter-lived than the CCC++. Not enough to test the quantitative prediction at a precision that would reveal whether the theory is correctly accounting for all the relevant physics. For that, you need tens of thousands. For the CBC+ and the CBB+, where the production rates are lower by factors of 10 or more, you need a detector collecting data at luminosities the current LHCb cannot tolerate. You need upgrade too. Gershon said, "Try our best." He meant, the current detector will search, and it will find something if the sensitivity permits. And if it does not find something, the absence of signal will at least constrain the production rate. And none of this will replace the measurements that the upgrade would have made. Try our best is the phrase of a physicist who knows his instrument's limits and respects the difference between what is reachable and what is not. Something else sits above the specific particles in the hierarchy of what is at stake. Something that connects the CBC+ and the CBB+, not just to QCD tests, but to a question that LHCb was designed from the beginning to address, and that the CCC+ family illuminates in a new way. The universe contains more matter than antimatter. This is not a subtle asymmetry. It is a total one. Every atom you have ever touched, every star you can see, every galaxy and every photograph taken by every telescope ever built is made of matter. The antimatter that the universe contained in its first instance after the Big Bang has almost entirely vanished. The small amount that physicists produce in accelerators and detect in cosmic rays is a rounding error compared to what the Standard Model predicts should have existed in roughly equal quantities at the beginning. Why there is more matter than antimatter is one of the deepest open questions in physics. The Standard Model does predict a small asymmetry between matter and antimatter, an asymmetry called CP violation, which refers to the combined violation of charge conjugation and parity symmetry. CP violation was first observed in kaon decays in 1964, confirmed in B-Meson decays in the early 2000s, and studied at LHCb with increasing precision throughout its operational history. In April 2026, just weeks after the GCC+ announcement, LHCb published new results on CP violation in B-Meson decays, penguin decays as physicists call them, referring to a specific topology of the Feynman diagram that showed a 4 sigma tension with the Standard Model prediction. Not a discovery, a tension, but a tension that adds to a pattern of B physics measurements that has been growing for a decade, each individual result below the 5 sigma threshold, but collectively pointing in a direction the Standard Model has difficulty accommodating. The matter-antimatter asymmetry that the Standard Model predicts is real, but far too small to account for the universe as we observe it. Something beyond the Standard Model must have produced the imbalance that allowed matter to dominate. Finding that something requires finding where the Standard Model's predictions for CP violation and for rare decay rates disagree with measurements at a level that exceeds what can be explained by theoretical uncertainty. That search is LHCb's core mission. It is also deeply connected to the doubly heavy baryon program, because the same heavy quark expansion that predicts doubly charmed baryon lifetimes also predicts B-Meson and B-baryon decay rates and CP asymmetries. Testing the expansion in the cleanest possible environment, the doubly heavy baryons, where the diquark structure separates the calculation, provides confidence in the same theoretical machinery being used to predict the B-Meson decays that are being compared against measurements in the search for new physics. Everything connects. The GCC+ lifetime, the GBC+ mass, the B-Meson CP violation measurement, the Standard Model tension announced 6 weeks after the GCC+ discovery, These are not isolated measurements in different corners of particle physics. They are facets of a single coherent program, testing QCD and the electroweak sector at different levels of precision, looking for the place where the standard model fails. LHCb Upgrade 2 was designed to advance every one of these measurements simultaneously, because the improvements to the detector, the higher luminosity, the better resolution, the more efficient trigger for hadronic modes, benefit all of them, not just the doubly heavy baryon program. Withdrawing the upgrade funding does not pause one measurement. It pauses all of them, at the moment when the pattern of tensions in B physics is becoming too consistent to ignore. At the moment when the first doubly charmed baryon measurement from the upgraded detector has just demonstrated that the instrument works exactly as designed. At the moment when the standard model anomalies that LHCb has been accumulating for a decade are approaching the threshold at which they would become discoveries. On 19 December 2025, Ian Chapman, Chief Executive of UK Research and Innovation, sent a letter to CERN's management. The letter told them that the UK would no longer provide the funding it had committed to for LHCb Upgrade 2. The project had been awarded £49.4 million in 2022, following a proposal submitted in 2021. About $5 million had been spent on the pre-construction phase, agreements with international partners, engineering designs, components ordered, commitments made that cannot be unmade by returning the letter. The remaining $44 million, committed and then cancelled, left a gap at the center of the upgrade's financial model that the international collaboration could not absorb without UK involvement. The letter arrived 3 days before Christmas. The LHCb collaboration was not consulted before it was sent. Tim Gershon said, "It was a complete shock." He said, "The LHCb collaboration were not asked for any input before the decision was made." And he said the thing that nobody in any official communication said, "It's like paying to heat your house but then sitting outside in the cold." Chapman's letter had noted that the UK would continue paying its CERN membership subscription, implying ongoing commitment. Gershon's analogy addressed this precisely. The membership subscription pays for the accelerator, the electricity, the tunnel, the infrastructure. It does not pay for the experiments. A country that pays for the building and forbids its researchers from using it is not participating in physics. It is subsidizing physics for other countries. Vincenzo Vagnoni, writing in Research Professional News in his capacity as LHCb spokesperson, described what this decision meant for the collaboration beyond UK borders. LHCb Upgrade 2 was formally proposed in 2017. Every plenary session of funding agencies at CERN since then had heard UK delegates from STFC reiterate unwavering support. Partner countries across Europe, France, Germany, Italy, the Netherlands, Switzerland, Brazil, and others had built their national roadmaps and their own funding commitments around the assumption that the UK would be central to the upgrade, as it had been central to everything LHCb had done since the experiment began. When the letter arrived in December, those international partners faced an impossible choice: increase their own national contributions substantially to cover the British shortfall, on a timescale dictated by the Lake's schedule and the long shutdown 4 installation window, or watch as an experiment into which they had already invested millions found its scientific reach curtailed. By suddenly pivoting, Vagnoni wrote, UCRI has created a destabilizing funding vacuum. It was a fundamental betrayal of more than 2 decades of scientific leadership and a blow to the foundational stability of European big science. Without UK funds, Gershon said, the project would be dead, not because the physics stopped being possible or the detector stopped being buildable, but because the schedule imposed by the LHC's operational timeline does not have room for the years it would take to find an alternative source of funding at the required scale. The high-luminosity LHC upgrade installs during long shutdown 4, with a fixed timeline. If the LHCb Upgrade 2 detector is not ready for long shutdown 4, it does not get a second chance at the same scale. The window closes. The experiment, which was expected to operate until 2033 in its current configuration, stops then. The high-luminosity era of the LHC, The decade of the 2030s, when proton-proton collision rates will be 10 times higher than they are today, passes without LHCb fully participating. The measurements that only LHCb can make do not get made. Paul Howarth, president-elect of the Institute of Physics, described the withdrawal of funding as incredibly damaging to the UK's international reputation as a science superpower and potentially causing long-term damage to the UK economy. He was specific about the economic claim. An earlier upgrade to the LHCb experiment generated approximately £15 million in contracts for more than 80 UK companies, through the demand for precision engineering, custom electronics, advanced materials, and specialized manufacturing that detector construction requires. LHCb Upgrade 2, had it proceeded, would have generated a similar pattern of industrial contracts. That economic return is not hypothetical. It is the documented outcome of the previous upgrade, now being cited as evidence of what the next upgrade would have produced, in a conversation about why the next upgrade's funding was withdrawn. The formal setting in which this conversation took place, the place where the consequences of the funding decision were most clearly visible, was a committee room in the Palace of Westminster. Early in 2026, the House of Commons Science, Innovation and Technology Select Committee convened to investigate the scale and impact of the proposed cuts to physics and astronomy research. The witnesses included Michelle Doherty, Executive Chair of STFC, Simon Williams, a postdoctoral researcher at the University of Durham, John Butterworth, Professor of Physics at University College London, and others. The committee chair was Chi Onwurah, the MP for Newcastle upon Tyne Central. The session on 4 March 2026, 2 weeks before the GCC Plus announcement, produced a series of exchanges that illuminate the gap between institutional account and practical consequence more clearly than any press release has managed. Doherty told the committee that the STFC needed to reduce spending by at least 30% compared to 2024 and 2025 levels. The total shortfall was approximately £162 million over 4 years. She cited inflation, rising energy costs, and unfavorable currency movements. The STFC pays its CERN subscription in Swiss francs, its share of other international facilities in dollars and euros, and the depreciation of sterling over recent years had added more than £50 million per year to its effective cost base, without any corresponding increase in its budget allocation. She said she had not been aware of the scale of the shortfall when she took up the role of executive chair in January 2025. It was not, she said, what she had signed up to. Doherty told the committee that STFC's position did weaken the UK's international standing, certainly. She said withdrawal from the LHCb upgrade was one of the specific decisions that produced this weakening. She said she wanted to have an open and honest conversation about how STFC funding was structured, specifically about whether international subscriptions should be separated from the grants budget, so that the rising cost of subscription commitments did not continue to erode the funding available for UK researchers to do science. She was describing a structural problem, a fixed, rising external commitment eating into a flat domestic budget, with no mechanism to absorb the difference except cuts to grants. Simon Williams sat before the committee as a postdoctoral researcher in theoretical particle physics, one of the 30 or so early career researchers who could not get grants to continue their work because TFC had delayed its grant decisions while it planned how to respond to the forthcoming cuts. The delay was administrative. Its effect was identical to a denial. A researcher whose contract ends in 6 months cannot wait for a funding body's internal planning cycle to complete. The uncertainty that has been injected into the system has been catastrophic, Williams said. He said there were essentially no STFC consolidated grant-funded postdocs beginning in 2026 in his area. The situation for early career researchers, he said, was almost too late to fix for this year. He described what happens when early career researchers leave. The skills and knowledge they carry leave with them, and the experimental programs that depend on those skills, the detector operations, the data analysis, the calibration work that makes a measurement like the GCC Plus possible, lose the human infrastructure that keeps them running. The tree, he said, is being killed by removing the roots. John Butterworth told the committee that by the time the funding situation improved, Doherty had suggested 2 years, it would be too late for some things. Specifically, this is such good science, he said. We would probably try to get back in there, but we would not be leading it anymore. That distinction, participating versus leading, is not vanity. It describes who sets the scientific agenda, who does the analysis, who trains the next generation, who the international collaboration looks to for technical decisions. The UK has been the technical engine of LHCb for a decade and a half. Leadership in a large collaboration is built through accumulated contributions, through institutional memory, through the presence of researchers at every level of the organization who know how the experiment works and are trusted by their international colleagues. That leadership cannot be purchased in a lump sum when funding is restored. It has to be continuously maintained, or it disperses. Chianwura asked Chapman for a comparison of curiosity-driven spending before and after the UCRI reorganization. Chapman said at first that this comparison was not possible to produce. When pressed, he agreed to provide a written breakdown. When it arrived, Onwurah found it insufficient for the purpose she had requested. The committee was very disappointed to learn that we couldn't actually track how that funding was changing, she said. The breakdown doesn't give us the level of detail we really need to be able to say, for example, is curiosity-driven research in particle or nuclear physics being cut or not? An institution managing £8 billion of public research funding annually was unable to demonstrate to a parliamentary committee, in a form the committee found satisfactory, whether it was protecting the category of research it was publicly saying it was protecting. The internal minutes of the STFC Governing Council described the Council's own head of strategy, characterizing the situation as a major shift of funding from curiosity-driven research to priority areas and targeted programs. When Chapman was asked directly about this characterization, his own council's internal record of what its head of strategy had described, he called it a misstatement. The internal description said, "Major shift away from curiosity-driven research." The public testimony said, "We are protecting curiosity-driven research." The gap between these two characterizations is not a matter of emphasis or framing. It is a direct factual contradiction. Science Minister Lord Valence told the committee that the cuts to early career researchers were a mistake, and that the government was working urgently to release funding. He described the situation as a prioritization process. It is not right to portray this as a massive cut to things, he said. It's about managing a budget responsibly. He added that the UK was and would remain the second largest funder of CERN. The second largest funder assertion and the LHCb upgrade withdrawal are compatible. They describe different things. CERN membership and experiment upgrade contributions are separate budget lines. You can be the second largest CERN member while withdrawing the funding for the upgrade that would allow the detector you partly built to continue operating in the era the LHC is about to enter. Both statements can be simultaneously true. Only one of them matters for whether the GBC Plus gets measured in the 2030s. The physics that the cancelled upgrade would have enabled is not abstract. It is a list of specific measurements, each one requiring more data or higher luminosity than the current detector can provide, each one testing the standard model at a level that the current dataset cannot reach. The GCC Plus lifetime has not been measured. 915 events establish existence in mass. They do not provide the decay length distribution needed for a precision lifetime measurement. Full Run 3 data will provide thousands of events, enough perhaps for a preliminary lifetime with significant uncertainties. Whether those uncertainties will be small enough to meaningfully test the ratio predicted by the heavy quark expansion, the factor of roughly 6, between Chi-CC plus and Chi-CC++ lifetimes, depends on how many. Thousands of events are accumulated, and on how well the systematic. Uncertainties from the selection procedure can be controlled. The selection biases the sample toward longer decay lengths. This bias requires correction from simulation, and the correction carries its own uncertainty. The mass measurement reported in March 2026 already absorbed a systematic uncertainty from the unknown lifetime. Because the decay length cut used in the selection creates a bias in the reconstructed mass that depends on the true lifetime. The mass is now known, the lifetime is not. The two measurements are coupled. More events help with all of this. The current detector will accumulate them, but accumulating enough events to push the lifetime ratio measurement to the level where it would test the theory at the precision that reveals whether the heavy quark expansion is correctly treating the doubly charmed baryon family, that requires tens of thousands of GCC plus events, produced in conditions where the trigger and selection are optimized for both members of the isospin doublet simultaneously. And then there are the particles the current detector cannot reach at all. The GBC+, 2 quarks, 1 beauty, 1 charm, and 1 up quark. Predicted mass approximately 7 giga-electronvolts. Never observed. Production rate in proton-proton collisions roughly a factor of 10 lower than the GCC+, because beauty quarks are produced less often than charm quarks at any given collision energy. Decay chain more complex. Lifetime different. The two heavy quarks in the GBC+ are not the same species, so the interference effects are different from those in the doubly charmed baryons, and the calculation must track a different set of diagrams. Searching for the GBC+ with the current LHCb detector is possible. Finding it is a different matter. Gershon said the word out of reach. He was not pessimistic. He was accurate. The GBB+, 2 beauty quarks and 1 up quark. Predicted mass approximately 10 giga-electronvolts. Even lower production rate. Even more complex decay chains. The most precise possible test of the heavy quark expansion in the doubly heavy baryon sector. Inaccessible with any detector currently operating or currently funded to be built. The Omega CC+, 2 charm quarks and 1 strange quark. Predicted mass between the two GCC baryons. Unobserved. Within reach of the current LHCb detector in principle, requiring dedicated analysis and more data. Its observation would complete the lightest tier of the doubly heavy baryon spectrum. Its lifetime, compared against theory, would add a third data point to the comparison that currently has 2. The comparison with 2 points tells you approximately where the theory lies. The comparison with 3 points begins to test the internal consistency of the theoretical framework. Each one of these measurements is a step in a program. None of them is the destination. The destination, the point at which the precision comparisons between theory and data reveal whether the standard model is complete, or whether something beyond it is required to account for the behavior of doubly heavy baryons, is downstream of all of them. The current detector reaches a fraction of the way there. LHCb Upgrade 2 was designed to finish the journey. It was designed to operate at luminosities that would produce a data sample corresponding to at least 300 inverse femtobarns of proton-proton collision data, compared to the roughly 7 inverse femtobarns collected in Run 3's first year. The physics program that 300 inverse femtobarns enables, described in the LHCb Upgrade 2 Discovery Potential document submitted to the European Particle Physics Strategy Update in 2025, includes all the measurements listed above plus a comprehensive program of B physics measurements for CP violation and rare decays that would test the standard model at a level of precision that could confirm or refute the tensions that have been accumulating throughout the LHCb Run 2 and Run 3 datasets. The document existed. It was written. It was submitted to the strategy process. The science was described in detail, with numerical projections for what the upgrade would achieve for each measurement. The upgrade was funded. The money was awarded. The pre-construction work began. And then the letter arrived in December. What the letter arrived into is a specific institutional landscape that is worth describing as clearly as the physics. Because the landscape determines whether the physics gets done. UK Research and Innovation manages £8 billion of public research funding annually across 7 research councils, including STFC. In early 2026, UKRI introduced a reorganization of how it categorizes and allocates its funding, dividing research into 3 broad buckets, oriented respectively toward curiosity-driven basic research, government priority areas including artificial intelligence and quantum computing, and applied research with direct business applications. The reorganization was presented as a way of aligning UCRI's portfolio with the government's economic agenda, making the funding more strategic and more legible. The consequences of this reorganization for particle physics and astronomy became visible almost immediately. STFC's budget, which had been held relatively flat in cash terms, rising from £835 million to £842 million between 2026 and 2030, was in real terms being eroded by the inflation and currency effects described above, and the reorganization appears to have directed additional resources toward the priority area bucket rather than the curiosity-driven bucket in ways that are, by the committee chair's own account, currently impossible to track from the published data. The STFC announced cuts of up to 30% to its particle physics, astronomy, and nuclear physics grants program. The LHCb upgrade, the electron-ion collider contribution, 2 national facilities all cut on a December timeline without community consultation. Curiosity-driven research, the kind that produced the Proton discovery in Rutherford's Manchester basement in 1917, the kind that produced the J-psi discovery in 1974, the kind that produced the Higgs boson discovery in 2012, the kind that produced the Chi-CC++ discovery in 2017, and the Chi-CC+ discovery in 2026, does not produce visible economic returns on the timescale of parliamentary terms or funding cycles. The electron was discovered in 1897. It took decades before electronic technology existed. DNA's double helix was described in 1953. It took decades for genomic medicine to emerge from it. The Higgs boson was predicted in 1964 and found in 2012. Its applications, if any, have not yet been identified, and the search for them was not the reason it was found. It was found because understanding the mechanism of mass generation in the Standard Model required knowing whether the Higgs field existed, and knowing that required building the LHC. The argument for funding curiosity-driven research is not that it generates economic returns on a 10-year horizon. It is that it generates the foundational knowledge that everything else is eventually built on timescales that no funding committee has the patience to wait for, and that the knowledge only exists if people are paid to pursue it without a predetermined destination in mind. The bucket system categorizes research by its expected destination. Curiosity-driven research, by definition, does not have a predetermined destination. Categorizing it accurately as such, and then deprioritizing it in favor of research whose destination is specified in advance, is not managing a budget responsibly. It is choosing not to invest in the kind of thinking that produces most of what we know. Williams made this argument to the committee with specific numbers rather than principles. A British-based company was already using results from his quantum computer calculations of subatomic particle behavior, calculations he had begun as pure research, with no application in mind, and that had found an application on a timescale of years rather than decades. The curiosity-driven work had produced a commercial output. If the research is removed from the country, he said, I have a strong belief that the industry will be removed from the country. He was not making an abstract point about the long-run social return to basic research. He was describing a causal chain with a specific example, drawn from his own career, with a company name attached. The chain was operating. It was being severed. The Select Committee chair wrote to Chapman and Valance describing the cuts as wholly unacceptable and demanding swift and decisive action. As of March 2026, the funding had not been restored. The upgrade remained unfunded. The collaboration was exploring alternatives. No alternative had emerged at the required scale. There is a shape to all of this that is easy to miss when looking at each element separately. In 1 year of running, the upgraded LHCb detector found the GCC+, the particle that had been missing for 23 years, that had been carried in the literature as a wrong number from CELEX for that entire period, that required a rebuilt instrument to resolve. The result was 7 sigma, 915 events, 3,619.97 mega electron volts. The Selex number, 3,520, wrong for 23 years, unretracted, was finally and completely displaced. Chris Parkes used the phrase "closes the door." The door is closed. In the same week, the committee chair described the accounting system as unable to track the funding category that was supposed to be protected. The head of UCRI described internal council records characterizing the funding shift as a misstatement. The science minister described cuts to early career researchers as a mistake, while describing cuts to experiments as a prioritization process. 30 physicists could not get grants. The international collaboration spokesperson described the UK's withdrawal as a fundamental betrayal of more than 2 decades of scientific leadership. The instrument's next phase had lost its funding. The person about to take over as LHCb spokesperson was simultaneously preparing to celebrate the most significant discovery in the experiment's recent history and trying to explain to a parliamentary committee what it meant that the funding for what comes next was gone. Gershon, that week, quoted the head of UCRI's own words back at him. Chapman had said, in describing the reorganization, "I really hope that in time this transition makes it very clear what we are trying to achieve." Gershon repeated this sentence to Physics World. He was generous with it. He was also precise. The sentence contains the entire problem, that the intentions are stated one way in public testimony, described differently in internal records, expressed differently again in outcomes, and the people working inside the system are left hoping that clarity will eventually arrive while the decisions that cannot wait for clarity, the career choices of 30 early career researchers, the engineering timeline of an upgrade with a fixed installation window, the planning schedules of 11 partner countries who now face a funding vacuum, are being made without it. The tree is standing, its roots are being removed. The fruit that appeared in March 2026, a 7 sigma peak, 915 events, a particle confirmed at last at the right mass after 23 years of searching and a wrong number in the literature, is real and extraordinary and exactly what the instrument was rebuilt to produce. The next fruit requires a deeper root system. The system is being removed while the current fruit is still being celebrated, in the same week, by the same people, from the same budget. The Selex number is still in the physical review letters, 3,520 mega-electronvolts published in 2002, never retracted. It sits there in the same archive as 3,619.97 mega-electronvolts, announced at the Morian Conference on March 17, 2026. The 100 mega-electronvolt gap between them constituting its own kind of answer to a question nobody formally asked, about a particle that was being produced and decaying inside accelerators for 2 decades. Invisible not because it was not there, but because the instruments available could not read where it was. That is what it costs to know something, not in the abstract. In the specific, years of searches shaped by a wrong coordinate, null results accumulating without resolving the claim, researchers designing analyses around a number that turned out to describe nothing real, and then a rebuilt instrument arriving with sufficient resolution to find the particle where it always was. That is the cost, distributed across careers and years, absorbed without acknowledgement, because it is not the kind of cost that appears in a funding report or a parliamentary testimony or a press release. The cost of not continuing to know something is different. It is not distributed. It is a gap, a measurement that is not made, a lifetime ratio that is not constrained, a GBC plus that is not found, a pattern of standard model anomalies that is not resolved, a generation of physicists who learned to build and operate and analyze the instrument, and who found somewhere else to work in the year when the grants did not come through, and whose skills went with them to the institutions in other countries that still funded what they did. Gershon will become LHCb spokesperson in July 2026. He will lead an experiment that has just demonstrated, in 1 year of running, that its rebuilt detector works at the level its designers intended, producing discoveries that required a decade of data from the previous generation. He will do this while managing the consequences of a funding withdrawal that was announced without consultation, that threatens the experiment's ability to participate in the most productive era of the LHC's operational history, and that arrived in the same week as the experiment's best result in years. He said, "No other experiment either running or planned will be able to do this physics." He said it as a fact about the detector's geometry, about the concentration of beauty and charm production at forward angles, about the 40 years of accumulated expertise in building and operating instruments optimized for flavor physics. He said it in the same sentence as the word "unfortunately," which is doing an amount of work that its 3 syllables cannot fully contain. The particle lived for less than a trillionth of a second. It was produced in the beampipe of the Large Hadron Collider in 2024 at a distance from the collision point smaller than a human cell, and it decayed before the detector could see it directly. The detector saw the aftermath, 5 charged particles spreading outward from where the CC+ had briefly been, and from those tracks working backward through geometry and momentum and particle identity, and the precise angles of light emitted in a cesium fluoride radiator medium, it reconstructed what had existed for less than a trillionth of a second. 915 times, across 1 year of data collection, this reconstruction succeeded. 915 events, pulled from a dataset of billions, pointing to the same invariant mass, with a significance of 7 sigma. A small sharp peak in a histogram. A number that was wrong for 23 years, and is now right. The wrong number will remain in the literature. The right number sits alongside it. The 100 mega-electron-volt gap between them is its own kind of answer. Quiet, permanent, and arrived at through a rebuilt machine that crossed a precision threshold its predecessor could not, finding the ghost of a particle that was there all along. What comes after that peak is the rest of the story. The lifetime measurement. The Omega CC+ search. The Xi-BC+, if the instrument can reach it. The Xi-BB+, if the upgrade is built. The standard model tests that become possible only when enough of the family is known to compare lifetimes and masses at the precision the theory requires. All of this exists, downstream of the peak, as a program of physics that is now partially open and partially foreclosed, depending on decisions being made far from the detector by people who are doing their best, which is the same thing every physicist in this story has been doing, and which has produced, in one case, a 7 sigma discovery, and in another, a gap in a funding schedule that may prove irreversible. The detector keeps running, the data keeps accumulating, the heavier cousins wait.